Hello dear students, in this lecture we will discuss about the method we can use to measure heart rate and average RR interval. So let's begin. We have Pantompkins algorithm. Actually, this is a method which we mainly use to detect the QRS complexes in an ECG signal. That is a extension of derivative based method that already we have discussed. So in this method actually this algorithm was proposed by Japu Pan and Willis J. Tompkins in 1985 in the journal IEEE Transactions on Biomedical Engineering. It is, as I mentioned, it is commonly used to detect the QRS complexes in the ECG signals. As we know that QRS complex represent the ventricular depolarization and the main skipe visible in an ECG signal, basically it represents the QRS complex. This feature, that is a mains or we can say large spike, makes it particularly suitable for measuring heart rate, and it is the first way to assess the heart health state. So this algorithm is based on the analysis of slope, amplitude and width of these QRS complexes. The Pan-Tompkins algorithm applies a series of filters to highlight the frequency content of rapid heart depolarization, and it also removes the background noise. Finally, it squares the signal to amplify the QRS contribute, and it then applies or uses adaptive threshold to detect the peak of filtered signal. Previously, we have discussed about this thing, but in that we were not using adaptive threshold. In that we were using a constant threshold, mainly 1. But in this we are using adaptive threshold to detect the peaks of the filtered signal. So this is the journal block diagram of Pan-Tompkins algorithm. As you can see in this we have first thing is again filter. But in this we are using band pass filtering, and that we are implementing by keeping in cascade the low pass filter and the high pass filter. So this makes the band pass filter. Then we have derivative operator, then we have squaring, and finally moving window integration. We will discuss the function of each part in detail. So starting with the low pass filter. Low pass filter is a recursive filter and it has integer coefficients to reduce the computational complexity. So you can see the transfer function that corresponds to a low pass filter. As you can see Hz, that is 1 by 32. Then in numerator you have 1 minus z raised to power minus 6 whole square, and then in denominator you can see you have 1 minus z inverse whole square. And if you find the equation of output, that is yn, in terms of xn using this equation, how we can do that? We can keep hz as yz by xz, then cross multiply both the sides and finally take the inverse transform. So you will get equation as yn equal to 2 times y of n minus 1 minus yn minus 2 plus 1 by 32, and then you get xn minus 2x of n minus 6 plus x of n minus 12. Basically what we have done in this is, you can see we have implemented the square. So in numerator you will get 1 plus z raised to power minus 12 and minus 2 into x, or we can say z raised to power minus 6. Similarly, we have done in the denominator. So you can get the equation as this. Now, with the sampling rate being 200 Hz and this filter has a cutoff frequency of around 11 Hz and it introduces a delay of 5 samples, or we can say 25 milliseconds. The filter provides the attenuation greater than 35 decibels at around 60 Hz, and it effectively suppresses power line interference if it is present. Then coming over to the high pass filter. It is implemented as a all pass filter minus the low pass filter. So the low pass filter for this has a transfer function, as you can see, HLP, ZLP means low pass. Then we have 1 by 32. In numerator you have 1 minus Z raised to power minus 32 divided by 1 minus Z inverse. So this is a equation for low pass filter to make high pass filter. And if I want to write in terms of y and x, we can write as, again, by keeping hz as yz by xz and then cross multiplying and getting inverse, you will get the equation as yn equal to y of n minus 1 plus xn minus x of n minus 32. So how we can get now this high pass filter equation? So we are considering this high pass filter as all pass filter minus this low pass filter. So the equation is z raised to power minus 16 minus 1 by 32, then transfer function of the low pass filter. So this is how we are implementing this high pass filter, and we are keeping both these high pass, and we have studied the last slide, this is low pass filter, we are keeping in cascade finally to make the band pass filter. So the output of this high pass filter, if you want to realize in equation, or I can say output input terms, so that equation will be x of n minus 16, which corresponds to z minus 16, this one, and then minus 1 by 32, and finally you will keep the equation of this low pass filter, that is y of n minus 1 plus xn minus x of n minus 2. So by this you will get the equation for high pass filter, and this high pass filter has a cutoff frequency of 5 Hz and it introduces a delay of around 80 milliseconds. Then next, after this filtering operation, keeping in cascade the low pass and high pass filter, which finally makes the band pass filter, we have the derivative operator. So derivative operation, you can see the equation yn is equal to 1 by 8 2 times xn plus x of n minus 1 minus x of n minus 3 minus 2 x of n minus 4. This is a derivative operator, and approximately this is an ideal d by dt operator which is valid up to 30 Hz. And this derivative procedure suppresses the low frequency components of the P and T waves, and it provides a large gain to the high frequency components arising from the high slopes of the QRS complexes. Then next part is squaring. This squaring operation, it will make, as we are doing the square, so every negative value become positive and positive will remain again positive. So this squaring operation will make the result positive, and it emphasizes large differences resulting from QRS complexes, and the small differences arising from P and T waves, they are now suppressed. So the high frequency components in the signal, they relate to the QRS complex because they are further enhanced. Now the next step is integration. The output of a derivative-based operation, it will exhibit multiple peaks within the duration of a single QRS complex. So this algorithm of integration will perform smoothing of the output of the preceding operations through what it will use is, it will use a moving window integration filter. And you can see the equation of that. It is yn is equal to 1 by n, then x of n minus in bracket n minus 1 plus x of in bracket n minus again n minus 2, so it will reach up to xn. So this is moving window integration filter. And the choice of the window is what capital N, you can see we have to choose. That will be depending we have to choose that length keeping in mind so many things. Like first thing what we have to keep in mind is we can't choose too large value, because if we choose a large value it will result in the output due to the QRS and T waves being merged into each other. And if we choose a small value, what it will give? It will yield several peaks even for a single QRS complex. So accordingly we have to choose that value for capital N. And in this research they kept window width of capital N equal to 30, which was found suitable for the sampling frequency of 200 Hz. So you can see in this figure it is also giving some delay. That is because of the whatever components and operations we have applied, it will also introduce some delay, but it will give the width of the QRS complex. Then after that we have to use adaptive thresholding, and this thresholding will adapt to changes in the ECG signal by computing running estimates of the signal as well as the noise peaks. So we can say that a peak is detected whenever the final output changes direction within a specified interval. And to reduce the possibility of wrongly selecting a noise peak as a QRS peak, we are keeping two thresholds in this, threshold 1 and threshold 2. So they will categorize whether the detected peak is a QRS signal, that peak corresponds to a QRS complex, or it is maybe due to some noisy artifact. The peak amplitude is compared to a threshold, that is threshold 1, that takes into account the available information about already detected QRS signal level, or we can say the noise level. So we are using signal level 1, or we can say noise level 1, that is already detected from the available information. So you can calculate threshold 1 as it is equal to noise level 1 plus 0.25 in bracket signal level 1 minus noise level 1. So here noise level 1 is the running estimate of the noise level in the integrated signal, and signal level 1 is the running estimate of the signal level in the integrated signal. Then the threshold and signal and noise levels are automatically updated after detecting a new peak based on its classification, whether it is a signal or a noise peak. Because it is adaptive thresholding, so we have to continuously update this threshold as well as signal and noise level peaks. So how we can update that one? So signal level 1, it can be calculated as 0.125 peak 1 plus 0.875 signal level 1. Similarly, the noise level 1 as equal to 0.125 peak 1 plus 0.875 noise level 1. So where this peak 1 is the new peak found in the integrated signal. Now at the beginning of the QRS detection, a 2 seconds learning phase is needed to initialize these levels, means to initialize the signal level 1 as well as the noise level 1 as a percentage of the maximum and average amplitude of the integrated signal respectively. Now, if a new peak 1 is under the threshold 1, then we will update the noise level. And if this peak 1 is above the threshold 1, the algorithm, what it will do, it will further check before confirming that this peak is a true QRS peak, taking into consideration the information provided by the bandpass filtered signal. So it will cross check that one, and then the threshold will be updated depending upon the levels we have taken from the filtered signal. So threshold 1 will be now updated to threshold 1 1, noise level f plus 0.25, that is into signal f minus noise level f. So f here denotes that it is for the filtered signal, and threshold 1 2 the second will be 0.5 into threshold I1. Now the signal level f, it will be 0.125 peak f, that is now from filtered signal because it is cross checking basically. 0.875 signal level f if this peak f is a signal peak, and it will use noise level f if that peak f corresponds to a noise peak. So in this way we can update the threshold as well as the signal levels. Now this signal level 1, it will be changed to this function. We can say it will use signal level, here you can see the coefficient, it is now 0.75. This will be updated or it will be changed when we are checking using threshold 1 2 rather than threshold 1 1. So this QRS is detected in the search back procedure using threshold 1 2, then we will use this formula instead of the previous formula. Now what is this search back procedure? The Pantompkins algorithm, it maintains two RR interval averages. One is RR average 1, other is RR average 2. So RR average 1, it is the average of the 8 most recent beats, and RR average 2 is the average of the 8 most recent beats having RR intervals within the range specified by RR low limit, that is given by 0.92 into RR average 2, and the upper limit, or we can say the higher limit, that is RR high limit, which is given by 1.16 into RR average 2. Now, whenever we can say a QRS is not detected for a certain interval specified as RR missed limit, which is also given by 1.66 into RR average 2, then the QRS is taken to be the peak between the established thresholds applied in the search back procedure. So this is when we will do this, when we will miss that QRS for a specified interval. Now we will see one illustration first of Pantompkins algorithm. Then we will see how it can be used to measure heart rate. So first figure, if you see, it shows the trace of an ECG signal, and then it is the output of a band pass filter. So band pass filter is applied to increase the signal to noise ratio, and this filter has the bandwidth of 5 to 15 Hertz, and it is suggested to maximize the QRS contribution and to reduce the muscle noise, baseline drift, power line interference, and also the P or T wave frequency content. Then the third figure, if you see, it is the of derivative operator, which further suppresses the P and T waves, you can see, and it provides a large output at the QRS locations. Then next, if you see the squaring operation enhances the large values and also it boosts the high frequency components, but the result will have multiple peaks. Now you can see these multiple peaks, and these needs to be smooth. So we need the smoothing operation, and for that now we are using integrator. So the final output of the integrator is a single smooth pulse for each QRS complex, and this figure is showing around 100 times of that actual integrand output. And if you see, we have a shift between the actual QRS and the pulse output due to the cumulative delays of the various filters. Now, next is how you can apply this algorithm for the measurement of heart rate. The intervals between two consecutive markers, where we have detected the QRS complexes, it gives the RR interval, which could be averaged over a number of beats to obtain a good estimate of the interbeat interval, and the heart rate may be computed in beats per minute as 60 divided by the average RR interval in seconds. The heart rate may also be obtained by counting the number of beats detected over a certain period, say around 10 seconds, and multiply the result with the required factor. Here it is 6 to get the number of beats over 1 minute. Now let's see one illustration. So for that, consider a ECG signal with high frequency noise, as you can see in this figure. Then the first figure in this shows the filtered version of that noisy signal. So noisy signal was filtered with an 8th order Butterworth low pass filter with a cutoff frequency of 90 Hz and sampling frequency of 200 Hz. And the second figure, if you see, it shows the output of the Pantompkins method, and this output is normalized by dividing its maximum over the data recorded. In this, what we are using a fixed threshold of 0.1 and a blanking interval of 250 milliseconds for successful detection of all the beats in the signal. And in this, if you calculate, the RR interval is computed as 716 millisecond, leading to an effective heart rate of 84 beats per minute. Now let's take one more illustration. For this, again, we have considered a noisy signal, ECG signal, sampled at 200 Hz. You can see in this figure, it is showing the first signal, it is showing the noisy ECG signal. And then we have used again the band pass filter to remove the low frequency artifact in the signal. And if you see the final output, it is showing two peaks. This, you can see this peaks. It is showing two peaks much larger than the others. If you see, all other peaks are small in amplitude, but these two peaks are larger in magnitude. One at the beginning of the signal, this is due to filtering artifact, and also other at 7.5 second due to an artifact in the signal. Now what we are doing is, we are applying the peak searching algorithm, and it will result in detection of 46 beats. If you count these are total 46 beats, and it is one more than the 45 present in the signal due to artifact at about 7.5 second. So this will be the extra beat which is due to artifact. So the average RR interval computed in this is 446.6 millisecond, leading to an effective heart rate of 137 beats per minute. So this demonstrates the need for pre-filtering the ECG signal so that it can remove that artifact, and also to apply an adaptive threshold so that we can continuously change the signal and amplitude levels depending upon the output of the filtered signal. So this is all in this lecture. For the reference, again, you can refer to the book Rangaraj M. Rangayan, Biomedical Signal Analysis, a Case Study Approach. So for now, thank you so